I'm recording this video right now in the summer of 2020, and I'll probably use it for many years, so this is going to change, but the textbook I'm currently using, they talk about rational functions in sections 3.5 and 3.6. They separate them out into two sections, and I choose to just cover it in a single set of notes, is what you have here. So if that's the textbook you're using right now, if you're in those classes, then this is covering two sections of the textbook. But we're talking about rational functions, different things about rational functions. And rational functions have asymptotes. So I'm going to start with the simplest rational function I can think of, 1 over x, so that I can numerically talk about what is an asymptote, what is the idea here, and then we'll just extend that to more complicated functions. So 1 over x just means to do the reciprocal, right? If you take 1 over 1, you get 1. Plug in 10, you get 1 over 10. Plug in 100, 1 over 100. So it's pretty easy to see that if I plug in larger and larger numbers, I'm just getting 1 over that number. I'm getting tiny fractions because they have huge denominators. Like if I plug in 1,000,000, I get 1 over 1,000,000, or 0.5 zeros and a 1. Okay? So as my x's get bigger, my y values are going towards 0. So y equals 0, which is the x-axis, winds up being a horizontal asymptote. And the same thing happens on the other side. If we plug in negative values going toward negative infinity, my y values still go towards 0. They're just negative values getting closer and closer to 0. So it turns out the x-axis, which is y equals 0, the y values are going toward the x-axis. So y equals 0 is a horizontal asymptote. So a horizontal asymptote is a line that as x goes to infinity or negative infinity, your y values start approaching, getting closer and closer and closer to. They'll never get to 0 for this function unless we round, but they'll get arbitrarily close. So we could plot some of those. You can't plot them all because they start getting arbitrarily close, and we couldn't physically draw that. So here I've plotted 4 positives and 4 negatives and then filled it in. We're going to talk about what happens in the middle in a minute, but filled in the curve with arrows on the end. So when we have an asymptote, it's important to draw arrows on your graph on the end when you're drawing them by hand. And I went in with the computer and made sure I had them here in the picture to show the arrow tells me it keeps going, and it's going to follow the arrow and just get closer and closer and closer to the axis. Okay? So as we go toward infinity or negative infinity, left to right on that graph, the y values are approaching y equals 0. Something similar in a way happens as we approach x equals 0. We get a vertical asymptote on the y-axis. Again, 1 over x is really just the reciprocal. If you plug in 1, you get 1. If you plug in a half, 1 over a half is 2. Plug in a fourth, 1 over that is 4. Plug in a tenth, 1 over that is 10. So the y values are getting arbitrarily large now. If I plug in 1 over 1,000,000, getting really close to 0, I get 1,000,000 for my y value. So as x goes to 0 from the positive side, we're going off toward infinity. And the function's undefined at 0. The domain of 1 over x is all real numbers except 0 because we can't divide by 0. But I like to say the graph blows up at 0. It goes off to infinity or negative infinity. On the negative side, same thing happens, but the numbers are all negative. The graph's going toward negative infinity as we approach 0 from the negative side. So the y-axis, in this case, is a vertical asymptote, a vertical line that the graph is approaching. So we could fill in some of those points and finally fill in the graph. We have arrows going toward each axis. Okay? The y-axis is a vertical asymptote. The x-axis is a horizontal asymptote. So in summary, an asymptote is a line that when you get to a certain point, the graph starts approaching it, either vertical or horizontal. And we'll even talk about slant asymptotes at the end of this section where the line is slanted. You can cross a horizontal asymptote. Your polynomial will never cross a vertical asymptote because it's undefined at the vertical asymptote. But the horizontal asymptote tells you what happens on the ends of the graph as x gets large. We'll see examples where you actually cross a horizontal asymptote in the middle but approach it on the ends of the graph. And there's the picture that my calculator made when I plotted 1 over x. Calculator doesn't do very good jobs with asymptotes for lots of reasons because it just plots points. But we need to draw the arrows on the end to see what's really happening. So again, a rational function is a ratio of two polynomials, p of x over q of x, where those are both polynomials. And the domain of that is all real numbers except where q of x is 0. And if you want to find the asymptotes, in algebra we can use some rules here to find them. The vertical asymptotes come from when the denominator is 0, assuming, as I have in bold at the bottom, that your polynomials are factored and reduced, that they're reduced. like in terms of numbers, 2/4 is the same as 1/2. You want reduced polynomials. Like if I had a factor of x plus 1 on the top and bottom, I would cancel those. You actually get a hole in the graph when that happens, not an asymptote. So if your polynomials are reduced, the values that make the bottom 0 are where you get vertical asymptotes. The horizontal asymptotes are a little more complicated. That's what happens as x gets large toward infinity or negative infinity. That gets into the idea of what are called limits, which are kind of the building blocks of calculus later on. But for polynomials, we have a nice little degree rule to see what happens. And we can think about it intuitively about what happens here. So I've set up these two polynomials where n is the degree of the numerator, the polynomial on top. M is the degree of the denominator on bottom. So it says if n is less than m, then r has a horizontal asymptote on the x-axis at y equals 0. Like 1 over x, that's degree 0 over degree 1. When the degree on the bottom is bigger, what happens is the bottom goes off toward infinity faster, and you go toward 0, just like 1 over x did. I'm going to skip down to c. When the degree on top is bigger, the top's going to win, and it's going to go off to infinity, because the top's going to get bigger and bigger faster than the bottom. When the degrees match, they kind of tie as you go off toward infinity, and you wind up getting everything else cancels, and you just get y equals a sub n over b sub n. And remember, if n equals m, it's the same subscript there. Okay, you get the ratio of the leading coefficients. And we'll see examples of each of these as we go through the notes.